So, hello all, very good evening. Thank you for joining on Day Masterclass. Today's day 6. So, thank you for joining. So, I'm warmly welcome to you. So, yeah, good evening to all. Samita, good evening. Krishna, Kalyani, Kallu, good evening, sir. Good evening to ma'am. Bobby Jose, hi. So, Jane Singh, good evening. Stilata, good evening. So, Dr. Bharat Raj Singh, good evening to sir. So, good evening to Danu. So, very good evening to all. Thank you for your presence in this session. So, good evening to all. So, let's wait for few minutes. So, wait for remaining people have to join. So, let's wait for few minutes. So, Havinas, Saini, good evening. Charishma, good evening. Avinash, good evening. It's good evening to all. Welcome back. Tumsi, good evening. So let's start. Let's get into session. So today we are gonna see combinational circuits. So and we will try some encoder, decoder, RTL code in Verilog. So we will write in this session. So and we will see the combination circuits like half adder, full adder, subtractor, full subtractor, and then mux, demux, and encoder, decoder, priority encoder, priority decoder. So we will see in this session. So we are going to write only two code, or we will try to write code for minimum two logics like encoder or decoder. So we seen already yesterday, we seen also some mux logic code. So that is a basic same way we have to follow in this way. So in this session, so we are going to use behavioral model styling Verilog code. So if you want to write in behavioral Verilog style code, you just know about behavior of the circuit. If you try any circuits, like if you try any logic circuits like a combinational circuit, sequential circuits, you must know the behavior of the circuit. So if you know the behavior of the circuit, you can easily write the logic for your RTL code. So that is the main thing. So you must know circuit and how to circuit works, how it works. So if these all things you know means you can write the RTL code in Verilog. So let's see. So yeah, good evening to all. Akshay, Sisha, Jivita. So and then Arun Tati. So welcome to all. Pallavi, good evening. So let's get into session. So before going to the start combinational logics, so have you ever wondered about how the sound system like a home theater, speaker, or subwoofer it works? So have you ever wondered about how it works? How they give sound like front and back and bass. So it will give. We know that some the DTS sound like a 5.1, 7.1 Dolby Atmos, or 5.1 DTS sound in home theater in theaters. So have you ever wondered about how it works? How the sound are separated, like a front speaker, back speaker, front left and right, back left and right, center, bass, master sound. So this comes under the DSP. So what is the logic they are using? So what is the logic works behind the sound systems? So op-amps also one of the technical answer. So I need from solution from combination logic circuits. So combination logics. So we are using one logic for these sound systems like so try to answer in chat box. So op-amps also used for the sound systems to converting the some signals. Amplification also, we can use sound amplification to increase the sound, and so it's like it comes under the power alternatives like that way. So I'm asking I'm just asking logic, what logic they are using to separate the sounds. So front speaker sound, back speaker sound, front, left and right, and then center. So these are the sounds we can feel in home theater, or if you see in any movie in theaters, you can notice this kind of sounds. One sound will come from your back side, one sound come from your front, left side, right side, so like that. So basically, decoder. So decoder is a one logic. It is used to decode the signals. So if you, for example, if you having on TV, if example, if you imagine you have TV in your home, so you have a home theater in your home. So output of TV is only one sound. So we are giving to input to home theater. So it will divide, or it will decode the sound. Like if you having the 5.1 home theater, it will divide, it will decode the sound according to the 5.1. It means front, left and right speaker, back, left and right speaker, center. So this decoding, so this is a decoding logic basically home theaters or sound system are using, so are used. So this is the logic behind the sound system in our daily life. So yeah, good evening to all. So this is the logic. So we are using the decoder logic for the sound system. So and also we are using the decoder and encoder for memory address transition. To decode the memory address, to encode the memory address, we have to use for decoder encoder. So let's see the what is functionalities, how to write the basic decoder encoder encoder Verilog code in EDA playground. So 8D songs, how they work. So basically all decoding, all song like a 5.1 8D song, I think it all comes based on logic of decode only, I think so. So decoder only, it will decode the signals. So name itself having the decode. So we having the only one input, and we will get the several outputs based on the decoding condition logics. So I think 8D sound also based on the decode logic. So you will refer yourself and let me know in upcoming session. So we'll go to the session. So basically, combination logics. So we know that combination logics are mux, demux, adder, full adder, encoder, decoder. So it is the digital circuit where the output depends on current input. So this is the basic definition of the combinational circuits. Output depends on the current inputs only. So it won't depends on previous input. So sequential circuits depends on previous output and the current inputs also. So previous output and current inputs it's used for sequential circuits, but the combination circuits it's only depends on current inputs only. So where the output is depends on present current input. So this is the definition for combination logic, combination circuits. So let's see the one by one of the combinational circuits. So like we know that half adder. So this is a circuit for half adder. So this is a truth table for half adder. So we have sum and carry. Half adder, by using half adder we can add two binaries. So two binary inputs, so A and B. So if you, this is a truth table, if you add the A and B, if you add 1 and 0, you will get sum 1 carry 0. So if you add 0 and 1, you will get sum 1 carry 0. If you add 1 1, so you will get sum 0 carry 1. So this is the logic of half adder. So this is the basic things. I hope you guys are know about this half adder. This is easy only. So and then we'll move to the full adder. So full adder is we already seen in previous sessions. Full adder needs 3 inputs A, B and carry in, and also it will give output like a sum and carry. So we can make a design. If you add two consecutive half adder, we can achieve the full adder functionalities. So this is that. So the inputs are three inputs, A and B, C in. So if you add 0 0 1, you will get some 1 carry 0. If you add 0 1 1, so if you have inputs like two hot ones, so two hot one means if you are having the 0 1 1, if say from the three inputs, if you have two ones means you will get some 1, sorry, some 0 carry 1. So you can see 0 1 1 some 0 carry 1. So if you add three ones like in your inputs like a 1 1 1, you will get some 1 as well as carry also 1. So this is the basic thing of full adder, basic logic. So and then we'll move to the binary addition. So we know that if you add means this is the consider 32-bit address we are used to add 28-bit numbers. So basically you can add this. This is a input A and input B. So we are previously having some carry output, it may be 0 or 1, so based on our previous carry output. So if you add this means you will get some 1 and then you get carry, so it will goes to other another like this next addition. So if you add this you will get some 2 carry 2 like this. So some 1 carry 1 here, some 2 carry 2 here, some 3 carry 3, we will get of the MSB, most 16 MSB bit. So these are the basic addition in binary. So and then we'll move to the basic rules of binary subtraction using half subtractor. So main difference is, so if you subtract 1, like you can see here, if you subtract 0 from 1, so when 1 is subtracted from 0, a borrow is taken from next most significant bit by making it 0. So you can see here, so if we are subtracting 0 minus 1, so we can't do subtract here, so we are borrowing the borrowing digit, so borrowing the values or any bit, so up from the most MSB bit. So this is LSB bit and this is MSB bit. So you can see here, this is LSB, this is MSB. So we do subtracting here 0 minus 1, so we can't subtract here. So I'm just borrowing the MSB bit 1 here. So it means 1 0, it means 2. So 1 means minus 1, so 2 minus 1, our output will be 1. So that one here you can see. So and then here I'm taking the 1, it makes 0. So I'm take out the 1 here for the this subtraction, and it will have the 0 here. So I'm taking the 1, so normally it will have the 0 here. So this is the subtraction logic. So this is a 3-bit binary subtraction. So you can see here, so if you can see consecutive of 2 of subtractor, we can make a full subtractor. So this is the circuit diagram for that. So you can see here, if you take any one example, so this is A and B, so 0 minus 1, so we can do, so we taking the neighbor we taking MSB, like we take borrow 1, so you can see borrow in 1, then difference is 0, then borrow out is 1. So this is the basic full adder circuit logic. So and then we'll move to the 4-bit adder cum subtractor circuit. So this is the circuit for 4-bit adder cum subtractor. So here you can see selection line. If selection equal to 0 means this circuit will do the addition operation, 4-bit adder. If the selection is 1 means it will do subtraction operation. So if you take for example, you can see if I'm using s equal to 0, so I want to do addition, so I'm just s equal 0, so it will have 0 here. So I'm just having inputs like a 1 1, so A0 B0 means it is my first inputs 1 1, so I'm just giving some random input like a 1 1. So and then you can see this 1 1. If you add, so I'm also s equal to 0, so 0 XOR of 1 XOR of 0, and then it will give some XOR operation, and then here a having the 1 input, it comes here, and then it will do some operation of full adder. So it will give XOR means 0 1. We having the different inputs for XOR gate. It will do the 1 here, 1 1. So here also having I given like a input equal to 1, so here it is also 1 1. So sum means we have another input for full adder, so I'm just given like a 0 for s, so it comes here. C carry in also 0, so this is the first carry in, so it having 0, it having 1 1. So if I add 1 1 0, it means sum 1 carry 1. So I will get the sum 0 is 1, and then carry 1. So carry 1 means it I'm just carry, it will applying for next full adder from MSP. So this is the circuit. If you pass some input from in the circuit, you will get the 4-bit Adder-Subtractor logic. So try it your own. So you just pass some logic like a 0 1 1 0 for the inputs, so we'll get the correct output, so based on our selection lines. So let's move to the n-bit triple carry adder. So basically n-bit triple carry adder is nothing but cascading of the full adders. So it will looks like this only. So input 1, this is the first full adder, so it having the inputs like A1 B1 C1. So full adder needs 3 inputs and 2 outputs. So if you add 4 bits, so if you add the, so like this is the 4 full adder, so 4-bit full adder, so you will get the 4 sum and then 1 carry. So this is the ripple carry adder looks like. So you can make any 5 ripple carry adder. 5, if you using the 5 full adder in the circuit, it is called 5 full adder, 5 ripple carry full adder. So but in this ripple carry, if you using the ripple carry adder, you may experience a delay. Why? Because of if you want to add third bit, means if you want to add third bit, you just need for previous 3 full adder must be complete. So this full adder depends on carry 4 input, so it must wait for these 3 full adder has to complete the execution, or complete the executions. So this full adder, so if you want to get firstly sum 4 and C5, so C5 is a carry out from the last full adder. So if you want to perform this only, so you must wait for these 3 full adder as to complete execution. So this is the one disadvantage in ripple carry adder. So it first full adder, it must wait for these 3 full adder as to complete the executions. For this we have the solution for that. For this delay, delay for calculating some, adding some in bits, so we just have the solution, that is a look ahead carry adder. So it is a fast adder, so it having some basic it having the different structure, adding the for adding the like 3 full adders. So here we having the 4 full adders. So if you want to do firstly second bit, you must wait for the first bit full adder operation, and then if you want to get a third bit result, so you just want to wait for these 2 full adder as to complete. So there is a delay in this look ripple carry adder. To rectify this, we have the look ahead carry adder. So this is the, we can call this also fast adder. So this is so it will look it look like this only. So but main disadvantage it is it has too many logical or combinational, it need too many combinational logics. Why? Because of, so you can see this is the uh, fast adder looks like how it work means it will look like this only. So firstly it have one full adder, so the inputs are A0 B0 C0, so mean A and B carrying. So we say carry, we can say like a C0, so you will get someone carry 1. And then you can see here for someone, so if you do second full adder, if you want to do operation of second full adder, you won't wait for this full adder has to complete. Why? Because of, you can see we have some combination logic. So here it having the inputs of A0 B0 C0, so it do the carry operation. What we get from this first full adder carry out, it will do some that same operation here. So you will get the carry of that this combination, so it will apply for the second full adder, you will get the sum 1 carry 2. So same thing, so you can see here for this full adder, it won't wait for these two full adders to complete. So it have own combination logic or a combination circuit. It having the inputs of A0 B0 10 B1 C0. So if it will do some combination logic, so it will give the carry operation of C2, so carry result of C2. So is C2 will apply for this full adder, you will get the S2 C3. So if you follow this circuit, there is no delay, so each and every full adder it is independent, so there is no dependent of the carry from the previous full adder. So this is the carry look ahead adder, so we can say is a fast adder. So this is the as a adder we can use it for the fast addition operations for fast adder. So this is the last circuit diagram for the fast adder. And then we'll move to look ahead adder. So we seen that. So guys, this is time for, if you guys are really interested, you can convert this masterclass 21 masterclass into 1 month internship. So internship on FPGA. So from this internship you will get the benefits of all 30 days recording session, all 30 days presentations, exclusive project codes, so you can also download yourself and you can store, so and then you will get the VIP community group for doubt clearing, and then internship updates. So and then you will get the internship confirmation letter from IETE. So you can get also 90 days LMS course access, and you will get the assignments, tasks, and you will get the weekly live session, so resume building, mock test, internship certificate, participation certificate. You will get all these benefits just for just 999. So our regular fee is 399. So in this masterclass time session period, we are giving at the discounted fee of just 999. So if you guys are really interested, you can join our internship program. So this is a pre-recorded detailed video sessions. So in the LMX, if you want means you can register for the internship. So this is internship registration link, and you will get also in chat box. Our organization will post the link on chat box. So this is a limited time period offer, so this offer will close 16th March. So let's see up next. So we're gonna see up now decoder. So already said no decoder, it will decode the signals from one input. So this is the functionalities of decoder. So it having the 2 power n output lines. If the so like if you input is 1 means, if you input is 1 line, if you want to decode means 2 power 1, so 2 power n is 2, so you will get the 2 outputs. So if you input line is 2 means you will get the 4 outputs, it means 2 power 2, so 2 power 2 equal to 4, so you will get the 4 outputs. This is the logic, 2 power n output, n is the input. So like so it is commonly used in digital systems for address decoding, memory selection, and data routing. So these are the like address decoding, memory selection, and data routing. So these are the fields we are using the decoder. So the decoder logic. So basically decoder works like in the combination circuit that converts a binary input signals into a one hot coded output. So one hot coded output means, so in your output it having the only one high. So if your output looks like 0010 so in your output it having only one bit as a high. So this is called one hot coded output. So yeah, so this is a decoder. So welcome guys, welcome, good evening to all. So I just seen some good evenings in the chat box. So we'll move to the decoder operations. So this is a general, it is also an interview questions. So if you are in some interview, you can receive question like design a decoding logic which gives an input 1 when the inputs are which gives an output 1. So you must get output 1 when inputs are 1 0 0 1. So it means if you want to, if they ask this question, you want to write the digital logic circuit for that, so you can try like this. So you can see, you can, so our question is design a decoding logic which gives an output 1. So output of a decode logic, it must get 1. So 1, so the inputs are 1 0 0 1. So you have to design, so what logic gate I have to use. So I'm using here this logic gates like a 1 0 0 1. So we know that AND gate will do multiplication. If either or one input is 0 means you will get a 0 output. If the all inputs, like if you're using 3-bit, if the all 3-bit inputs or all 3 input it must have 1, then only you will get the 1 output, like a high output. So for that the input is 1, so we need to add some NOT gate here. So this is a NOT gate symbol. So for that if using NOT gate, you can complete, you can give opposite of your input. So you can see 1 0 0 1. So it, after by using the NOT gate, I'm getting 1 here and then I'm getting 1 here. So I will given to this AND gate, so I will get the 1 as output. So it having 1 here, I think here is also 1 1 1. So 4 bit of 1 means in a 4 bit of AND gate you will get the 1 output. So this is the logic of the binary. So this is the answer for this question. So let's move on to another question. So you can design the decoding logic which gives an output 1 when the design input is when the input is 1 0 1 1. So this is a circuit for this question. So you will get it, you will just the inputs are 1 0 1 1, so you must get 1 as output. So you can try this circuit. So try to apply the stimulus or input for the circuit, you will get the correct answer. So basically, so we are entered into 3 cross 8 decoder. It means 3 input 8 outputs. We know that 2 power n logic we have to follow. So n equal to input, so input is 3, so 2 power 3 8. So we have the 3 inputs. So you will get the decoder 8 line outputs, like a 8-bit outputs. So you can see this is the 3 line input means you having the 3 inputs 0 0 1. This is a combination of the inputs. So like 0 0 1 0 0 1 0 1 0 0 1 1. So these are the combination of the inputs for decoder. So you will get the output like a 1. So this is a 1 hot output. So 1. So in this output you have only 1 bit as 1. So 1 bit as 1 binary 1 here. So you can see all this output you have only one bit binary, so binary 1, so you can see here. So every outputs, it contains only one bit binary 1. So this is the logic for the 3x8 decoder. It means 3 input, 8 outputs. So this is a decoder implementation. This is circuit look like this. So this is a decoder circuit. So this is a 4-bit decoder. So 4 power 2 means, sorry, 2 power 4 means 16. 4 input, 16 output. You can see 4 inputs. So like 4-bit inputs will get the 16-bit output. So we just see the application of the decoder. So you can see this some application, controller it having some decoder operation, binary decoder here. It will decode to it having some pins like first pin, second pin, third pin. It having 15 pins. So each and every pin having some applications like a printer, keyboard, monitor, modem, scanner, disk, so these are the peripherals we are using in computer. So we can use this is example for the decoder. So first pin is connected to printer. So if you using the printer, so it will your decoder, if you give some input, like if you give some address means it will choose this printer. If you give address means it will choose keyboard. If you give the address for the monitor, it will choose this decoder, choose the monitor. So these are the functionalities we have decoders. Based on our inputs, we can use these peripherals by using the decoder operation. So let's see some RTL code before going to start encoder. So in this session also I am going to use EDA playground. So this is EDA playground. So yesterday we seen. So before going to start so I hope you guys know the Verilog syntax. Yesterday we also written some code in Verilog. So just today also we are going to write Verilog code just in for the 4x1. So I'm going to write a 2x decoder. So 2 input, you will get the 4. If the input is 2, and you will get the 4 outputs. So 4-bit outputs, 2-bit input, 4-bit output. So module, my module name is I should also said, if you write a module name, so don't use number from the starting of the module name. You have to use for character. So decoder 2x4, and then n module. So this is syntax for the this is syntax in Verilog. So I'm going to write input and output signals of my decoder. So my inputs are, so I didn't have any circuit logic diagram for 2x4. So I just type. So this is my 2x4 decoder circuit look like this only. So 2 inputs and then 4 outputs. So 2 input means input 2 down to 0, 1 down to 0. It means 2-bit input. Just write in for the input, and then I'm going to use enable. So enable signal is 1-bit enable. If the enable is high means it will do operation of decoder. If the enable pin is low means it won't do decoder operation. It will it will just do default what we assigned for the output. So and then output is we will get the 4-bit output. So 3 down to 0. The output is out. So in this I'm going to use behavioral model style by using the always block, always at so I'm just first write the if condition for the enable. If enable is high means if the enable is high means it will do the decoding operation. So I'm going to use the case, it will easy to understand. So case in, so based on our input I will choose my I will choose my output. So if my input is 2 binary 0 is equal, so if my so sorry, so you can see here my input is 0 0. So if my input signal, so basically this decoder it having two signals, maybe first time it having 0 0 or A having 0, B having 0, in other condition A having 0, B having 1, and another condition A having 1, B having 0. So we have four conditions. If the first condition it will give D0 this output, and then if the second condition it will give this D1 output, decoder output. In the third condition it will give this D2 output. In the third condition it will give this D3 output. So I'm just write logic for that. So this is first condition and then binary 0 1 I will get 0 1 0. So I just copy this for the time saving. So and then so these are my conditions 0 0 0 1 1 0 1 1. So I will get the output, like I want to write the outputs what I will get. So this is the outputs I'm getting. If the inputs of A, like input we having the input it having 2 bits. If the 2 bits having 0 0, it will choose first decoder. This is second decoder output, this is the third decoder output, this is the fourth decoder output. So this is if condition, if enable is if this is the condition for if enable is high. Else, so if enable is low means I just write else condition, else begin end. So if you write one or more statements in the if, you have to write a begin end here. So inside the begin end only you can write a case, or you can write one or more statements. For that I am going to use here also else begin end. So if my enable is 0 means I will get my output as 4 with binary 0 0 0. So I will get this output. So if the enable is high means, so it will do decoding operation based on my inputs, like input signals. So if the enable is low means I will get output as 4-bit binary 0. So this is the design code. So I just save and run for check the errors. So and then I'm going to also write test bench for this. So I'm just change my simulator to Costa Sim. So I just got an error here, like in the 16th line you can see here in syntax error. So let's see what is the error. This you must have to close the begin end. So this end is for this begin, so this end is for this begin, so this end is for this begin. So I just correctly. So we missed that one, like a default and end case. Defaultly I just I'm just assigning the default condition for decoder is 4-bit binary 00 only. So and then end case. So I just save and run. So I'm used the out in the always block. So I have to use reg here. So yesterday also I set inside the, if you're using some signal inside the always block, it is an output means you have to write a reg in the port list. So I don't, if you can see I don't have any error. So and then I will move to write a test bench in module. So my signals are reg 1 down to 0 of in, and then reg enable. So enable is only 1-bit signal, and then wire for output. So my output is 3 down to 0, 4-bit output. So I just write here. So and then I am instantiating the design code with test bench. Yesterday I also said what is instantiation. So I'm just instantiating my code. For that I just write, I have to write my module name of my design code. It is decoder 2x4. This is my instance procedure, and then instance name A1. You can give any name of the instance name like B1 A1. So I'm just instantiating by the signals like a port. So for that you can also use start here. So dot start, it means automatically it will instantiation, but our regular way is writing the connecting by port, like input. This in is referred to current module input. This in refers to other module input like a test bench input, test bench signal. Inside the bracket I am writing in, this is refers to our design code signal. So and then en, this is my current module test bench signal. This en is my design code signal, and then out. So this is my current module, this out is my test bench design module signal. So I'm just instantiated my signals from, I'm just connected the test bench and the design code. So and then I will write the initial begin block to start my simulation. So it will start from here only. In this initial begin is the simulation time. In the simulation time, so I'm just printing, sorry. So I'm going to print the outputs. Monitor. So monitor is one keyword in Verilog to display the outputs in transcript. So and then I want to see also time in decimal. So I just use the modulo decimal. D means decimal, and then in binary, and also enable in binary, and also out in binary. So and then I want to see dollar time for time, and then in, and then enable, and then out. So this is the way of, this is printing like display statements in Verilog. so I give some delay here, and then I just pass some input signal for my design code. It is like I just enable, so I give one bit binary, one for enable. So I'm just, it means I give enable, I give one for enable, so it will do decode operation. So at the same time, after, so I will give the some delay, and then I give input equal to just I'm using these conditions like 0 0. So I just give, I want to check binary 1 0, like a third condition. I want to see third decoder output. For that I'm going to use binary 1 0. So I just given, so I just run this. Let's check I'm getting this value or not. So if I given like a input for input is 1 0, so I have to get 0 1 1. So let's try. Yeah, you can see my input is 1 0, enable is high, and then 0 1. So if you can see I just change here my enable equal to 0, 1 bit of 0. So I just give I just offed my decoder by using the enable signal, and I save this and then run this. Let's see what happens. So you can see my enable is 0, input is 1 0. Here also enable is 0, so that's why it giving output like a 0 0. So our default condition, or else, or if enable is 0 means I set some conditions, so I have to get like a 4 bit of 0. So I am received a 4 bit of 0. So my logic works correctly. So this is the way of writing 2x4 decoder. So you can also use 3x8 decoder also. So by using the 3 inputs lines, like it having 0 0 1 1, so 3 bit of inputs, it will you will get the 8 bit of outputs. So this is a logic for decoder. So you can also test the remaining conditions. I'm just passing some values. I just copy this. So my inputs are 0 0 0 1 0 1 1 0 1. So I just and then I changed my enable to 1. So you can see my outputs are, if 0 0 means it will give output like decoder output like a 0 0 1. 0 1 means I will get to 0 1 0. 1 0 means 0 1 1 0 1 0 0 1 1 1 0 0. So these are my output based on my condition in design code. So let's see the upcoming code. So we seen decoder, encoder. We see now encoder. So decode is the opposite operation of the encoder. So it will compressing the signals into required outputs. Like if you use 4x2 encoder means you have the 4 input and then 2 outputs. So this is the functionalities of the encoder. So let's see how it works. So you can see it having some number of inputs, so 0 to 9, so 10 inputs. So I can compress into 4 bits, so 4 bit of output. So this is the decimal 2 BCD encoder. So for the 10 bit of like a 0 to 9, 10 bit, so 10 inputs we can compress by using the 4 outputs, so we will get a 4 outputs. So this is the logic for that. So you can see the 4x2 encoder. So it means you will, if you give like a, these are the inputs, you will get output like this. So this is a 4x2 encoder operation. This is a circuit for that. So if your input means, if you input like a, if you give input for a 4x2 encoder like a 0 0 0 1, you will get output of 0 0. If you give like a 0 0 1 0, you will get a 0 1 output. If you give like a 0 1 0 0, you will get a 1 0 output. So this is the 4x2 encoder. So we are going to write code for this. So for that I just remove this conditions here also. So we know that 4 input 2 outputs, so it works like say 2 power like a n power 2. Sorry, it has some conditions like a encoder 2, I think 2 power n or 2n, I think so. So it if the 4 input means you will get the 2 outputs. 8 input means you will get the 3 outputs, opposite of the decoder. So I'm just going to write encoder operation. So my inputs are I have 3 inputs. So input, I have 4 input. So input 3 down to 0 in, and then enable signal. I am going to use enable signal. So this is a good way of writing code if you using enable or ready signal like that. So these are the status signals, and then my output is I'm going if I use 4x2 encoder, so 2 outputs, so 1 down to 0, so 2 bits, so I use 1 down to 0 here, out. So this is my port list. Since I'm using the always block at start, begin, end. So if enable is high means I will do the encoder operation. So begin it. So and then I'm going to use same here case statements based on my input. So if my input is, so we have 4-bit input, so I'm just write 4 tick binary 0 0 like that, low, like you can see here 0 0 0 0 1 0 1. It will you will get output of 2-bit binary 0 0 0. You can see also here 2-bit of binary 0 0. Same like for remaining 4 condition. So I just write here. So and then my other input is 0 1 0. I will get the output of 0 1, and then here 1 0 1 1 1, here 1 0 0 1 0 0. So this is my condition. So and then write a default. I just write default condition. My default condition out, I will get like a 2-bit of binary XX, so I can write anything. So and then end case, So in case, and then int, and I've already given int, and then else, I'm writing else for this if condition. If begin end, so so if the enable is 0 means I will get output of 0 for 2 bit of binary 0. So this is my condition. So this is a this begin is for this end for this begin, this end for this begin, this end for this begin. So this is the encoder logic of 4x2. So just run this and save for checking error. So I have 0 error. So I'm going to write a test bench here. So I just register my input signal like a 3 down to 0 for input, and then reg enable for single bit. So and then output is wire. So it is I have 2 bit 1 down to 0 of out. So and then I'm going to write instantiation. So just write encoder 4x2. This is my design module name, this instance name. So I'm just using a dot star here for time consideration. So it will automatically connect the test bench and design code. So I just write initial begin. So this is my simulation stimulus. This is the block for pass the stimulus to design code. So so just write a display statements here, monitor, and then so I want to see output in, I just see, I don't want to see our time, so just directly use the signals like input in binary, and then enable in also binary, and then output also I have to see in binary. So signals like in, you can see. So yeah, and then enable, and then out. So this is my display statements without time. I don't want to see time, simulation time. So just delays, I think I just add some delay. Enable equal to 1. So it means it will execute the encoder operation, and then I just pass some signals, inputs. Sorry. So input equal to 4 bit of 4 bit of binary 0 0 1. So this is my first input for my signal. So I just save and run this to see my output, whether it's giving correct output or not. So you can see my input is 0 0 1. I will get output of 0 0. It will give this output. So I can also give in the form of decimal. So you can see here 4 bit decimal. So you can see this 0 0 1, it's we can say in decimal like 1. This 0 0 1 0 we can say in 2. So I just pass 2. So this input is so we can write this like a 0 0 1 0 in decimal, we can write as 2. So I just pass the 2 decimal 2 as input, Yeah, you can see my why I'm getting the 0010 means in my display statements I written like I want to see in my output in decimal, sorry binary. That's why I'm getting the binary output. If I change to D here, so I will get the decimal output. So I just save and run this to see my decimal output in the format of decimal outputs. So you can see 2 and 1. So you can also see this is the binary form, this is the binary form of 2, this is the binary form of 1. So I will get the same thing. Input is 2, output is 1. So this is a writing of encoder, basic to 4x2 encoder. And you can also try your own self, like a 8x3 encoder and priority encoder and decoder also. So this is the logic for that. So this is the time, so you can convert this masterclass into 1 month internship. I already said no. So these are the benefits you will get the from internship. All the details, recording session, presentations, exclusive project codes, VIP community group for your doubt clearing and internship updates, and you will get the internship confirmation letter from IETE, and you will get the 90 days LMS course access, and you will get the assignment, task, weekly live session, resume building, internship certificates, and also you will get the participation certificates. These are all the benefits you will get at the 1 month of internship. So our regular fee is 3,999. So you will get at just 399. So you can use this link for registration the internship program. So let's move to the mux. So this is we already written some code in mux, like a 2x1 mux. So this is the basic operation of the like mux. We know that it will compress the input. So if you it will do if input is, so basically the mux is the device that allows digital information from several sources to be routed onto a single line of transmission. So it do like a compression. So it has several number of inputs. It just compress the signal into single one line or two line. So it is like combining together. It will give some one or two outputs. So this is mux functionalities. So basic mux has several data input lines and a single output line. For selecting the line, we have the selection. We have the another input like a selection pin. So yesterday or previous class we also seen mux code and how it mux works. So this is the 2x1 mux in example. It having the two input lines, one output line. So this is a selection line for the selecting the output lines. So if s equals 0, it will select first input. If s equal to 1 means it will select this input. So these are the mux functionalities we seen also. So this is a 4x1 mux. It having the 4 inputs and then one output. So based on the selection line, if we input like a 0 0 means it will select the first input like a first input line. If the selection line is 0 1 means it will select the second line. If the selection line is 1 0 means it will select this third line. If the select line is 1 1 means it will select the last line. So D3 input as output. So this is the mux equation. So by using this equation you can write the Verilog code by using this single equation, like equation only. By using assigned statements you can write this, but in your behavioral model we can write without knowing this equation. You must know the behavior of this circuit. So if the selection line is 0 0, it will choose first line. 0 1 it will choose second line. The 0 1 0 means it will select the third line. 1 1 means it will select the fourth line. So this is the behavior of this circuit. By using this behavior ideas we can write the RTL code. So this is the main advantage of the behavioral model style of writing RTL code, Verilog code. So this is a 4x1 multiplexer circuit, looks like this. So this is a 4x1 mux. We can see two selection lines, 4 inputs, 1 output. It 8x1. So we can also use enable signal for mux. So it is, if you using the enable signal in your code, it is very good design. Why? Because of I have some condition. If I switch it will works like a switch. Switch on means if a switch is on condition means it will do mux operation. If if it is on off means it will give some default value of the 8+1 mux. So if you are using the enable signal, ready signal in your code, so it will good sign you are writing the good RTL code. So and then you can see I'm here, it is the 4x1 mux. So why means I having the 4 inputs, my output is 1. So this is the 4x1 mux logic diagram, but I made this by using the 2x1 mux. So I'm just using 2x1 to make the 4x1 mux. So if using this like it having 4 inputs, 1 output, so it is based on 2x1. So here you can see I'm using the 3 selection line. So you can see 0 0 0 1 means it will choose D0 input, so this line. If the selection like 1 1 1 means it will select this. If the selection line is 1 0 1, it will select this. So if the selection line is 0 0 1, it will select this D1 as the output. So we can write the by using the 2x1 we can make 4x1 mux, and also we can make 8x1 mux by adding the other 2x1 mux like this. So by adding the 2x1 mux in your circuit, you can make 4x1, 8x1, 16x1, like 32x1 also we can make. By also using the 4x1, if using the 4x1 mux, you will get the 8x1 mux circuit. So this is also some mux feature. So by using the 2x1, like by using 4x1 and 2x1, I can make the full half adder circuit and full adder circuit. So if you give like if this is the example for the 4x1 mux, using it will do the half adder operation. So making half adder operation by using the 4x1 mux. So this is a logic like this. So like this, it having output like a sum and carry. So xy and this xy is act as a selection line. It will common for these 2 mux. You can see these 2 lines goes this mux also, and then this mux also. So it having the selection line for common 2 mux. 2 mux means 4x1 mux. So it having the outputs of the half adder. You can see this is half adder. So let's see output of half adder truth table. Yeah, you can see it having the 0 1 1 0. So this is the output, it having the input for 4x1, and also this is output for the carry of the half adder. So 0 0 1 0 0 0 1. So if I choose, my selection line is 0 0 means it will choose this, so it will choose this. So this is from this mux, it will choose this line, first line. In this mux it will choose this line. So if the inputs are by using, if you take an half adder operation of a 0 0, a equals 0, b equals 0, you will get the sum 0 carry 0. So you can see here it also we will get the 0 output for sum. Here it also we will get the 0 output for carry. So if we given like a 1 1 here 1 1, it will choose this line, and then it will choose last line. So 1 1 means it will choose this line. Here also it will choose this line. So if the half adder it inputs like a equal to 1, b equal to 1, you will get the sum 1, sorry, sum 0, carry 1. So you can see also here sum 0. This line, if you choose this line, means you will get the 0 output, so you will get the 1 output here. So we get correct output of half adder. So we can make any large half adder by using the 2x1 mux, sorry, 4x1 mux. So this is the same like the 2x1 mux to make the half adders functionalities. So these are the we can make. So if you know behavior of this particular circuit, you can use in mux, demux or encoder decoder to give the required output based on our behavioral ideas in Verilog. So we can write logic for this also in Verilog code by using the case statement, or if using the some assigned statements, you can use by using the case logic, we can write this logic in Verilog. So this is a thing I want to share in the mux perspective. So this is for today. So we'll see tomorrow. So thank you Arjay for your compliment. Very good, very excellent lecture. So tomorrow we'll see the sequential logics. So I think it is hard to cover all combination logic in one session, like in 1 hour class. So it will take one day also. So if you want to read, you read yourself sequential and combination logic. There's a lot of things you want to learn. So you have to learn about digital electronics, and you should also. So you have to learn like an encoder, priority encoder, priority decoder. That is a important thing in combination logics. So just read the priority encoder, priority decoder. So it will be helpful for your placements if you are studying in your college. So thank you guys, thank you for today, thank you for listening. So we'll see tomorrow. So tomorrow topic will be sequential circuits. So we will write some code for flip-flop latches, and then some other sequential circuits, SR flip-flop, JK flip-flop. So there. So thank you guys, thank you for listening. We'll see you tomorrow.